Welcome to This Explainer. Today, we're diving headfirst into an invisible, microscopic war that's literally happening right now on grocery store shelves everywhere. You might walk down the aisle and just see rows of snacks, but there is a highly sophisticated mathematical battle being waged to protect your food from an unseen enemy.
Okay, let's start with a totally universal and frankly deeply relatable disappointment. We've all been there, right? You buy a bag of potato chips, open it up a few weeks later, craving that perfect snap, only to find they've lost their crunch, and honestly, they just taste terrible. So why does this happen? Is it just time? Well, as it turns out, time is only part of the equation here.
Take a look at the drastic difference here between a fresh and a rancid chip. The real enemy isn't time itself, it's oxygen. When oxygen gets to your food, it kicks off a chemical process called lipid oxidation. And man, this is absolutely devastating for your snacks. It causes pigment degradation, meaning they literally lose their color, it strips away nutrients, and ultimately, it leaves you with that foul rancidity and totally ruined flavor.
So now that we know the stakes, here's our roadmap for understanding the fascinating science and engineering we use to actually solve this stale chip problem. We're going to cover the stale chip problem, how oxygen invades, the physics of diffusion, factors weakening the barrier, and finally engineering the perfect bag. Let's get right into it.
Moving right into Section 1, the stale chip problem. We really need to look closer at what happens when oxygen breaches our packaging defenses and why certain foods are basically just sitting ducks.
Potato chips are especially vulnerable here, and you might be wondering why. Well, it comes down to their geometry and their composition. They have this massive surface area exposed to the air around them, and they are packed with high fat content from the frying process, which, is what makes them delicious, for sure, but it also makes minimizing oxygen ingress absolutely essential. If oxygen gets in, lipid oxidation is inevitable, and the shelf life of the product just completely plummets.
Which brings us to Section 2, how oxygen invades. So how exactly does this enemy get past the packaging in the first place? You probably assume the bag is completely sealed, right? Well, not exactly.
You might think the main way in is through visible holes or micro defects in the bag or the seal, something we call pore permeation. But the mind-bending reality, and actually the primary way oxygen gets in, is through solution permeation. Get this, the oxygen actually dissolves right into the solid plastic matrix of the bag itself. It doesn't even need a hole, it just essentially walks right through the solid walls.
This stealthy intrusion happens in 3 distinct phases. First up is sorption, where oxygen molecules from the atmosphere dissolve into the outer surface of the polymer film. Second is diffusion, where they physically travel through the solid polymer matrix. And third is desorption, where they evaporate off the inner wall and enter the package's internal atmosphere. And out of these 3, it's that slow, arduous diffusion through the solid polymer matrix that acts as the primary rate-controlling step of the whole invasion. Let's see how this builds into the complete reaction pathway. Once the oxygen has desorbed inside the package headspace, the whole battle shifts. Following what chemists call Henry's law, the oxygen then dissolves straight into the food matrix itself, where it diffuses internally, and once it's inside the chip, game over. It actively participates in the chemical, enzymatic, and microbial reactions that completely ruin your snack.
To fight this invisible war, packaging engineers can't just guess. They have to turn to Section 3, the physics of diffusion.
Now, don't worry, you don't need complex math to understand this. Simply put, the concentration gradient is the driving force that pushes oxygen from the outside in. Think of it as a spatial imbalance. And nature absolutely hates an imbalance, because there's a lot of oxygen in the atmosphere and very little initially inside the flush chip bag. Nature wants to equal things out. This creates a literal physical pressure pushing oxygen right into the plastic.
According to Fick's first law, which describes steady-state diffusion, you can think of it kind of like a crowded room. The oxygen outside the bag is a packed, high-concentration room constantly trying to push its way into the relatively empty, low-concentration room inside the bag. Nature essentially acts like a bouncer here, pushing oxygen down a one-way street directly toward your chips until both of those rooms are equally crowded.
But, this diffusion isn't just a constant, steady march. The battlefield is totally dynamic. Let's look at Section 4, factors weakening the barrier, to understand how environmental changes can actually speed up the enemy's advance.
We really have to account for specific vulnerabilities here. For example, high storage temperatures give thermal energy to the polymer chains, causing them to wiggle, jiggle, and move much more rapidly. This creates temporary gaps, allowing oxygen molecules to diffuse extremely fast. It's kind of like giving the oxygen a VIP fast pass right through the plastic. Furthermore, low crystallinity in the plastic means there are more loose, amorphous regions for oxygen to easily slip through, as opposed to dense, tightly packed crystalline structures which would block their path. Even high humidity can act as a plasticizer for certain materials, basically softening the polymer and increasing that free volume space.
All right, let's dive into our final chapter, Section 5, Engineering the Perfect Bag, to see exactly how we build the armor to exploit these physical laws. Looking at the oxygen diffusion coefficient of various materials really proves why material science is the ultimate hero of our story. It shows exactly why we can't just use standard cheap plastics like LDPE or low-density polyethylene for long-term storage. I mean, its diffusion rate is just sky-high compared to the others. Instead, we need high-tech barriers like EVOH, ethylene vinyl alcohol, or metallized films, which have drastically lower diffusion coefficients. They are literally orders of magnitude better at stopping the oxygen march.
Because no single plastic does everything perfectly, a chip bag is actually a highly engineered, multi-layered fortress. The outer layer, made of materials like PET, acts as the stone wall. It provides mechanical strength so the bag doesn't tear. Then you have the core layer, using our high-tech EVOH or metallized PET, acting as the impenetrable moat that provides the crucial high oxygen barrier. Finally, the inner layer, which is often our cheap but easily melted LDPE, acts as the smooth courtyard, allowing the factory machines to heat seal the bag shut safely right against the food.
By combining these specific materials into these common multi-layer structures, engineers create custom packaging that, honestly, practically performs miracles. They simultaneously provide strong oxygen barriers to stop rancidity, moisture resistance to keep the chips crunchy, and the mechanical flexibility needed to survive a bumpy truck ride to your local grocery store. It truly is a symphony of polymer properties working perfectly together.
So, extending shelf life isn't magic at all, and it's definitely not just pumping the bag full of air, which, by the way, is actually nitrogen. Fun fact. As researchers note, the effectiveness of a packaging material depends strongly on its ability to resist oxygen transport. It's a precise, mathematically driven application of polymer science designed to entirely starve that internal environment of oxygen, stopping those chemical oxidation reactions dead in their tracks.
Hopefully this explainer has completely shifted your perspective. By showing you the incredible microscopic battles happening right in your pantry, you can truly appreciate the hidden science keeping your food fresh. Next time you crack open a fresh bag of chips, will you just see a snack or a literal marvel of modern engineering? It really makes you wonder, what other invisible engineering marvels are sitting quietly in the rest of your kitchen? Stay curious, keep learning, and I'll catch you in the next explainer.